Okay.
Yeah.
So welcome to this lecture by Sunil. He'll be continuing on Lorentz Group from the last talk. So this will be the last talk in this trimester, and next talk will start. Next series of talk will start on 16th of January by Professor B. Suri on algebraic groups.
Yeah. Thank you so much. So yeah. I will continue from where I was yesterday, but I will just briefly review a few things from yesterday, which I'll need for today. So the main point is that, okay, if we have, so we are going to look at this group, SO31 plus the proper Lorentz group, and we're actually going to look at its algebra, which is just the infinitesimal elements, infinitesimally close to the identity, those elements of the group. And because we are infinitesimally close to the identity, the thing becomes linear and we get a linear algebra. And the algebra relations I wrote last time, but I'll write them again, look like this. There's also a way to write it in terms of the full M mu nu, which generates all Lorentz transformations, but this form is more convenient. And in fact, even Harish-Chandra uses both forms, but in particular, always this form ends up being important. Now, one amusing fact from this is that you can't get rid of this minus sign. If you try to change the sign of k, nothing happens to this algebra at all, because here it's bilinear in k and here there's k on both sides. So either way, changing sign of k does nothing. Changing sign of j will remove this sign, but it will put it here and here. So either way, the fact that this sign is opposite of those signs is a basic fact of this algebra. And I believe that if it was not SO31 but SO4, then all would be plus. So this is the algebra. So that's the first observation. The next observation is that we define some quasi-legal things. I don't know what the correct term is, but we define complex combinations. This is, by the way, quite familiar also in just SO3. If you remember the Pauli matrices, sigma 1, sigma 2, sigma 3, we often define sigma plus and sigma minus, which are sigma 1 plus and minus I sigma 2. But really, we are not supposed to bring in I into the whole thing because all the coefficients are real. So we can do it as long as we keep in mind a little carefully what we are doing. And for example, we never, if you notice, we'll never exponentiate sigma plus or sigma minus. Okay, we always exponentiate e to the I theta dot sigma. If we exponentiated e to the I sigma plus, then I hope this point is clear. I'm just repeating something which in a way I said yesterday. In Pauli matrices, if I did this, this would be e to the I times say some parameter, then I would have e to the I theta sigma 1 plus I sigma 2. And now this term e to the sigma 2 comes with a minus theta, so it's completely unbounded. Okay, and that's not a part of the SU2 group at all. Okay, so this is what you have to understand, that we don't consider those, and we have to kind of realize in our mind, keep in our minds that we are not going to exponentiate these combinations. However, we can use these combinations to label things, to label representations, and because these form an, each of them forms an SU2, so each of them gives me, and same for, so they are decoupled SU2s. So NiNj also gives me Nk. All right. So now it's logical to label representations by. So what do we do when we have an SU2? This is SU2. In non-relativistic physics, we take this M, we call it J over there, and we this M has nothing to do with any M I introduced earlier. This M and N are these. But anyway, in non-relativistic physics, we call it J and we square it. And we note that the square doesn't commute, it does commute with everything. And it's called a Casimir operator. And now, again, there's a subtlety. You can't really square the element of an algebra because an algebra is a linear space. But if you have a representation, then it's a matrix that you can certainly square. Or if you want to do it in the algebra, you go to what is called the universal enveloping algebra, which allows products, formal products of these things. So either way, here we should label representations by their values of m squared and n squared. Okay. And the individual states of the representation will be labeled by the values of m3 and n3. Because I can pick one of the 1, 2, 3, M1, 2, 3 and N1, 2, 3, which will commute with these and won't commute with the others. So if I have picked 3, M3, then I can't pick M1 and M2 as a label because it doesn't commute. Okay. So therefore, the label in this language is J1, J2 for the representation and then M1, M2 for the corresponding state with minus J1 less than or equal to M1 less than or equal to J1 and same for J2. Okay, so these are a set of standard labels that you use for representations of the Lorentz algebra, inherited from what we already know to do in the case of a compact algebra, a compact group like SO3. Fine. But there's another way to label these, which is quite natural also. And this other way is quite useful in the discussion. So I'll introduce it. So if I have a pair of numbers J1 and J2, and I have a pair of SU2s, I can think of the diagonal SU2, which is exactly the, or a diagonal SO3, which is exactly the rotation group. Okay, you can see it from here because out of these, J's generate rotations and K's generate boosts. So the sub-algebra generated by J's is precisely the rotations. And here you can see that the diagonal of these, which means I basically add m with n, then K drops out and J remains. So it's m plus n is J. All right. So that J is the SO3 rotation group subgroup of SO3, 1. Okay. So with respect to the SO3 group, subgroup of SO3, 1, what should be, how do we understand these labels? And the answer is basically the same as the product formula for two values J1 and J2, the tensor product of two representations of label J1 and J2 of angular momentum J1 and J2 in a single SO3. And if you remember, this gives me J1 minus J2, a lot of, it's a reducible representation, and it gives me a lot of values of J going up to a maximum of J1 plus J2. Okay. And among all of these, if I focus on one irreducible representation, then there'll be a J which is bounded by these. And there'll also be an M which is between minus J and plus J. So therefore, I have four quantities J1, J2, J and M which label the state. Analogous to the four quantities, what did I say? I forgot to say one more thing. We give a name to this. This one we call capital J min, or some authors call it capital J 0. And this maximum value, I'll call it capital J max or capital J1. I'll use 0 and 1. You should not forget that 0 and 1 means min and max. Okay. So now what we are going to do is change from the labels J1, J2, M1, M2, where all the letters are small, to capital letters. So I should have taken all these to be capital. I'll just give it that name. Okay, and therefore my representation can now be labeled with J0, J1, J, and M. If you have ever studied addition of angular momenta, as it's called in quantum mechanics, you have used this umpteen times. I'm just repeating something which is very standard. Okay, that the representation obtained by tensoring an irreducible one of J1 and J2 is reducible. To pick an irreducible one, I must specify a J which is in this range. Okay, and then within that one, the M value will go from, sorry, completely wrong. Why is nobody stopping me writing nonsensical things? I'm very disappointed in the audience. How did you let this go? Ah, yes, there should not be. Please, please. I hate not being interrupted because then I just make more and more mistakes. So the claim is that this is just another relabeling of the old J1, J2, M1, M2. The same set of states spanned by those is the set spanned by these. Okay, but there's one more step when we study SO3, the rotation group. So far, if you see, nowhere have I said that anything is integer or half integer. Okay, and where does that come from? Do people know? What is the step at which you find that J in ordinary SU2? Where did I write ordinary SO3 or ordinary SO? I think I erased it. Anyway, so the J of any SO3 is 0, half, 1, 3 half. This you all know by heart, I think. At least the physics students surely do, but I think even math students, you have taken first year chemistry, quantum mechanics, and second year physics, quantum mechanics, and it is drilled into you that J is 0, half, 1, 3 half, and so on. But where does it come from? Or just a rule? Raising, lowering, yes, and what? Raising and lowering. Ah, excellent. Thank you. Finite dimensional. Okay. So the goal in the case of SO3 is to find finite dimensional unitary representations. And this goal is possible because being unitary is compatible with being finite dimensional for compact groups. But yesterday I described, stated and briefly described an argument that for a non-compact group, that isn't the case, that you can't have unitary finite dimensional representation. And the goal here is therefore to look for unitary infinite dimensional representations. Yes? No, not space, number of generators. Not number of just, no, neither number of generators nor space-time dimension, the size of the matrix. N by N matrix, that size, if you represent an algebra by matrices, the size of the matrix is the dimension of the representation. So for SO3, we have the 3 by 3 representation, that is the defining one of SO3, but we also have the 2 by 2, which is given by Pauli matrices. So that's a two-dimensional representation. And it represents a particle which has two possible spins up and down. So now we are going to look for infinite dimensional representations because that's the only thing we can expect to find if we wanted them to be unitary. Yes. Yeah. No, no, no. Both are representations of SO3 comma 1. So it's the same. These labels and these labels describe the same set of states. In principle, if I was a little more disciplined, I could have given you this lecture with any of either side. But since many of the references use this form, I've introduced this form. Otherwise, that form is perfectly natural. Yeah. Yeah. So it looks, that's right. So here it looks as if I'm taking two different J's of the same group. But actually, what I'm doing is taking J1 of the first SO3, this one, and J2 belonging to this one. Okay, all I'm saying is that because there are these two factors, so SO31 behaves like, for this purpose, SO3 cross SO3. It isn't really because of this illegal operation. If it was SO4, by the way, it really would have been SO3 cross SO3. But because of this thing, it's not really, but it behaves like, for representation labels, as SO3 cross SO3. And therefore, we have a pair of J's, and any pair of J's, even if they belong to different SO3s, I can replace by this. Okay, you can see why I can replace it, because after all, if I know J1 and J2, then I know all these numbers. But also, if I know the end point, Jmin and Jmax, then by adding and subtracting and making some assumption whether J1 is greater than J2 or other way around, I can get back J1 and J2. So I've actually not done anything new. And in fact, this sort of thing has been known for some time. So that's all I'm doing, just introducing this notation. Yes. Each of them is a representation of SO3. The tensor is a, okay, so if I treat it each one as a representation of the same SO3, then the tensor is again a representation of that SO3. What I'm doing, okay, so maybe I should have said this, maybe I did say it actually. So let's write it here. SO31 is, this means is like but not exactly. Okay, so this is the two SO3 algebras, the M's and N's. Okay, now these have a diagonal SO3, which is a sub-algebra of that. Okay, so if J1 is the representation of this SO3 and J2 of that one, then both are the J1 or J2 of this one because it's diagonal. And then this manipulation I can think of as being done in the diagonal SO3. I think that might be the clearest way to say it. Anyway, up to now I have done nothing but introduce some labels. Okay. Now one last thing which will be very useful is to ask, which I didn't do last time, what are the Casimirs? The quadratic Casimir of SO3, 1. So it's a maximal set of operators which are quadratic in the generators of the algebra and which commute with the whole algebra. Okay, and in the J and K form, which I just erased, it's easy to check that they are C1 equals J squared minus K squared, and C2 equals J dot K. Okay, and they have some expressions also in terms of the M's. So for example, J squared minus K squared is equal to twice M squared plus N squared, and J dot K is minus I M squared minus N squared. This is not very surprising. Of course, you can use either J squared minus K squared and J dot K, or you can use M squared and N squared. Okay, in this notation, it's obvious that M squared and N squared are the Casimirs because one of them is the standard Casimir of the first subalgebra and N squared is the standard Casimir of the second one. But it's also convenient to think of them in the J and K basis. If you're interested in the Lorentz covariant version, then this is half M mu nu, and this one up to a sign is like this. Okay, so these are the two Casimirs. Fine. Okay, now we'll proceed, and one little comment I want to make is that what did I want to say? The Casimirs of the inhomogeneous Lorentz group are completely different. Okay, the reason is yesterday this is not the main topic of my discussion, but yesterday I highlighted for you that the inhomogeneous Lorentz group, despite containing the homogeneous one, has very different representation properties. And one of the clear reasons is that the Casimirs are completely different. Neither of these is a Casimir of the full one, because it has to commute with everything. And in the inhomogeneous one, there is P, the translation generators, and it doesn't commute with either of these. In fact, the Casimir turns out to be for ISO, this is a side comment, the Casimirs are P squared, where P is the Paul momentum generator, okay, which is actually minus p0 squared plus p vector squared. This is C1, or one of the Casimirs, and the other is a very famous one, which is written like this. And this is called the Pauli-Lubansky vector. It's a square of, so okay, first you have to construct this, and then you have to square it. By square, I mean take the same thing with rho lowered and contract over rho. Okay, and this is called W squared. And this vector is a famous vector in quantum mechanics called the Pauli-Lubansky vector, and it plays a key role in classifying representations of ISO. Okay, so just to kind of, it helps me at least to realize why this world of ISO is a different world from the world of SO, and that's why Dirac's and Harish-Chandra's papers ignored Wigner, and Wigner also ignored them. Only Bargman, as I said, was in both camps. He started in this Dirac and Harish-Chandra camp with SO, quickly realized that he was in the wrong camp, so to say, from physics point of view, and switched to the other one. So that's a little bit of history. Okay, good. Okay, now I prepared all this to tell you about Harish-Chandra's work. But before I tell you about his work, I need to talk about Dirac's work. And before I talk about Dirac's work, I should tell you a story. This is not a personal story, but just to know what kind of person he was. He, I think, to some extent, quite purposely, was very, spoke very little as possible, and often took things literally, which were not meant to be taken literally. And two little stories. One is that he actually married Wigner's sister, but in the years thereafter, and Wigner and he were both top physicists. So in the whole science community, people dropping in at their houses and so on, they knew Dirac, they knew Wigner, and now there's this new person in Dirac's house. And every time a visitor came, he would say, "This is Wigner's sister," not bothering to mention that she was also his wife. Okay, he just continued calling her Wigner's sister. That was Dirac. And actually, at the Heritage School I attended, Dirac and Wigner's sister / Dirac's wife were all present. So I got to see this phenomenon. The other story about him is that he had a party at his home, and people who came over, this is British, so they make conversation about the weather. And somebody, comes into his living room and says, "It's very cold outside." The Dirac doesn't answer. He gets up from his chair, he walks to the door of his house, he opens it, looks out, closes the door, comes back, and says, "Yes." So this is now, in a way, this actually kind of personality shows in all his papers. They are very economical. They are almost always very short. I don't know if he ever wrote a long paper. Even his quantum mechanics textbook is shorter than most other quantum mechanics textbooks. And the point is, like, there's no chit chat. It's just the actual work is just done. Okay. Now the significance of this work, which is called the expansor formalism from 1945, it was the first paper which explicitly constructed non-unitary representations, unitary infinite dimensional representations of the Lorentz group. Till that time, people were satisfied with the non-unitary finite dimensional representations. And as I told you, this other track of Bargman and Wigner were doing the representations of ISO rather than SO. Okay, but Dirac wanted to know about unitary representations of SO. And he starts by saying why he thinks it's important. But in a sense, he was wrong, or at least so far he hasn't been proved right. He felt that it should be important in physics because unitarity is important in physics and SO31 is important in physics. But as it turns out, this work of his has really never found any application in physics. But it's a very beautiful work. And what is very nice is that I can show it to you explicitly because it's extremely simple to write. So I just did a little more. I worked out some of the details from his paper so that I could present them to you. So I'm going to first show you the expansor formalism for representations of O3. And I think, I don't know if this is newly invented by him, but it probably was inspired by things people had done. But it's very pretty and it's very cute. Okay, so let's do it. So the first thing we do is introduce three variables, formal variables. So you can take them to be complex numbers. We are never going to give them any values. The formal variable means we write functions of them and think of them as like generating functions or something. So we'll call them xi1, xi2, and xi3. And consider the series. So consider the function t of xi1, xi2, and xi3 defined as the sum. So it's like a multinomial in these things. So xi1 to the power a. A is not an index, it's an integer power, 0, 1, 2, 3, positive integer power. Xi2 to the b, xi3 to the c. And now we'll multiply it by some constant coefficients a, b, c. So as I said, it's like a generating function. This much is quite simple. But let's make the additional restriction that a plus b plus c equals n, some fixed positive integer. Okay. That means this is a homogeneous polynomial in three variables. So far, so good. By the way, Dirac did not initially make this restriction. He first starts with a, b, and c all going from 0 to infinity. This immediately should cause a bit of panic, because then how do we know anything converges? And he discusses, he has a whole section in his paper on convergence of that. But for my purposes, I think n is good enough. He also specializes to that later. And now let's see what use this series is. Okay. Now, before we do that, let's define a norm for this series. So the magnitude of this quantity t squared is defined to be the sum a factorial, b factorial, c factorial, the components a, b, c whole squared. Okay, summed over a, b, c. And automatically these a, b, c is because this is the definition of them. So they'll only be there if a plus b plus c is n, otherwise they are 0. So you can forget about restricting the sum. That's the norm. Okay. Now let's carry out a linear transformation on the xi i's. So I'm going to use I to label these. I goes over 1, 2, 3. And the reason it's 3 is that we are trying to represent O3. You can do this trick by replacing 3 with any other integer you like, and you'll get On. Okay. So let's perform a linear transformation. And Dirac likes to do it this way, which is also which is a way I also like. He says I simply take the xi and write them as functions of xi prime. Some people say xi goes to xi prime, which is a function of xi. Some people say xi is equal to xi of xi prime. And that is a little bit easier to do. And if we do this, then t, the same t that we started with, will become this one. This quantity will become summation a prime abc xi prime 1 to the a, xi prime 2 to the b, and xi prime 3 to the c. Yeah, so as I said, Dirac writes xi is equal to xi of xi prime. It's not a change of variables, but a substitution. You can always do it either way. It is roughly the active and passive way of doing changes of variable. But Dirac's way is to just choose psi to be functions of a new variable, but linear. That's important. Because it's linear and because this was homogeneous, these things will mix and you'll get some expression of this form. And now the claim is, so this is obvious and this is easy to work out because if I know what is psi as a function of psi prime, it's a matrix times psi prime. So I know that matrix. So I can put that here, here, and here. Then I take the psi primes and I take those three matrices and I combine them with A and I get A prime. So that's pretty obvious. Okay. Now his observation is if the transformation star preserves psi1 squared plus psi2 squared, the quadratic form, plus psi3 squared, which of course is the definition of O3. It's the set of transformations that preserve this sum. Then ABC is a representation of O3. Now it takes a while to even understand how to see that, but fortunately Dirac tells us exactly how to see it. So let me show it to you. In fact, I can work out one or two cases, then it will become clearer. So the reason you say it's a representation, okay, then there's a, sorry. Before I got there, I went too fast. Excuse me, please rewind a few seconds. The first thing Dirac does with this is to prove a theorem. And this is what gives the representation. Theorem says, if star, that transformation there, which writes psi in terms of psi prime, preserves psi1 squared plus psi2 squared plus psi3 squared, then mod t squared, as he has defined, remains invariant. Mod t squared is that thing up there. Okay. So the claim is that if the transformation psi to psi prime is a linear transformation preserving the quadratic form, then you do that linear transformation here, you compute A prime by that, then you put A prime here, and you just get the same sum. So t squared is preserved. So that's his main theorem of his paper. And he proves it by working with the infinitesimal transformation. So he says, let psi1 be psi1 prime plus epsilon psi2 prime, and let psi2 be psi2 prime minus epsilon psi1 prime, and let's not change psi3. Okay, so here's a linear transformation, and you can easily see that to order epsilon, this does not change the quadratic form. Then he plugs this in to this definition of t, okay, and he computes A prime, and then he puts it in that, and you can see readily that it's invariant. I won't do it for you, though I have it in my notes, and if I write them up, I'll put them in the write-up. But it's actually a very simple exercise that any of you can do. It's really very, very simple, and you can follow his paper. And here, the factorial factors are crucial, because what happens in this transformation is that you get some term involving A of A plus 1, B, and C. So then you have to shift A in the sum, and then you get an extra factor A plus 1, which converts this to A plus 1 factorial. Then after you shift A plus 1 back to A, you get the same thing back. I'm just giving you a very crude thing, but it's workable. Another warning is that, of course, these always start from 0, but after you make a shift, sometimes you'll get a negative. The series may start from a negative value, but it doesn't matter. because negative any integer factorial is 0. So that actually helps things a lot. The factorial of any negative integer is defined through gamma function, and it's just 0. So he makes all these points.
It's not 0.
Yeah. Let's see. It's a yeah. So okay, good point. Yeah, it's a pole.
For our definition, we are taking it to the 0.
No. He actually says, I better check what he says then. I hope I'm not getting this wrong, but in fact, yeah, you're quite right. It's divergent. No, I'm wondering whether you get 1 over, but you can't get 1 over a factorial here. Later we will, but here we don't. Okay, I take that statement back, and you can check what the correct statement is. Maybe it doesn't happen in O3. Maybe it happens only in O3 comma 1. And in that case, we'll see that the corresponding object has a factorial in the denominator. So I think that may be the correct place where this statement applies. Okay. Here, I think just by change of variables, you're going to get the answer you want. Okay. So T squared is invariant. Very good. Now, so once you have this invariant norm, then from here he proceeds. So this is the theorem of Dirac. So here from this he proceeds to argue that these coefficients A, B, C give a representation of O3. And he doesn't say it very explicitly, but it turns out to be a reducible representation. And he doesn't focus on irreducible at all in the paper. He doesn't simply ask the question about irreducible. So let's see how this works. So what are A, B, and C? They are the number of powers of psi1, psi2, and psi3, respectively, in this. And so Dirac sets up the following. He says, associate a tensor T I1 up to IN with A, B, C as follows. So for given value of A, B, and C, we have T with 1 appearing A times, 2 appearing B times, and 3 appearing C times. And since A plus B plus C is N, in our series we constrained it to have A plus B plus C equals N. Therefore, this tensor will have a total of N indices. So it will be a rank N tensor. Okay. And in this way, by looking at all the possible ABCs for all partitions A plus B plus C equals N, you will get all components of a symmetric tensor. So this will be a symmetric tensor. And to demystify it a bit, I'll show you the rank 2 case where it's extremely easy. So if N is 2, let's just do N equals 2. So if N is 2, then what A's am I allowed? So I have indices A, B, and C which sum up to 2. Okay. What are all the possible A, B, and C which sum up to 2? Well, I can have 2, 0, 0, 0, 2, 0, 0, 0, 2. I can have 0, 1, 1, 1, 0, 1, and 1, 1, 0. And that's it. All possible ways of taking. So I can't even turn on 3 of them because they have to all add up to 2. Okay. So as per Dirac's rule, I should associate this to the component T11 because this 2 means 1 appears twice. This 2 means 2 appears twice. This says T33. This one says 2 appears once and 3 appears once. So this is T23. This is T13. And this is T12. So I've got 6 components of a second rank tensor Tij. And if you accept that it's symmetric, then 2, 3 and 3, 2 are the same, 1, 3 and 3, 1 are the same, 2, 1 and 1, 2 are the same. So I've got all components. And in fact, a 2 by 2 symmetric matrix does have, a 3 by 3 symmetric matrix does have 6 independent components. So I'm done. Okay, good. So this gives me a symmetric tensor, and this is the symmetric tensor representation of O3 given by all symmetric matrices Tij for the algebra. Now the problem with this representation is that it is not irreducible. Why? Because there's a trace T equals delta Ij Tij with repeated indices summed over, and this is O3 invariant. If this transforms and this anyway is an O3 invariant, this thing remains O3 invariant. Okay, as a result, this is a singlet, and then you should consider T hat Ij, which is the trace subtracted part of T, so 1/3 delta Ij T, and if you take this one, then its trace is 0. Okay, and how many components does that leave? That leaves 5, and this is 1. And so we see that what we have recovered are the j equals 0 representation of SO3, which is 1-dimensional, and the j equals 2 representation, which is 5-dimensional. 2j plus 1 is 5. Okay, so the representation of this Dirac's expansor gives rise to reducible representations corresponding to symmetric tensors. Now it's limited in 2 ways. It only gives tensors and it only gives symmetric ones. But Dirac gives us a prescription to go beyond symmetric. He says you need to introduce more triplets of size if you want to. So there were 3 size precisely. He says have also eta 1, eta 2, eta 3, and alpha 1, alpha 2, alpha 3. And if you introduce enough of those, you can get non-symmetric tensors in this way. I haven't worked it through, but you can check that. The other limitation is that, of course, it is only tensor, these are only tensor representations of SO3, which are the only single valued representations of SO3, but doesn't give you the spinor representations, which are double valued in SO3. But first, of course, he hasn't solved any new problems so far because we already know everything we need to know about SO3. What we want to know about is SO3, 1. And now comes the what Professor Mukunda has referred to as the Dirac maneuver. So now he wants to extend this to SO3, 1. So you have to do something clever. You have to add the 4th direction. It's you can guess a few things. One is that this quadratic form will gain a minus psi 0 squared plus all these, right? That's the quadratic form of SO3, 1. That one you can guess. What should be the norm which is preserved? Unless you have a norm which is preserved, you haven't done anything. Okay. Now he notices that if I did introduce psi 0, so he says now we have psi 0, psi 1, psi 2, psi 3, and we write T as the sum A, B, C, D, psi 0 to the D, this is the new one, and the others are the old ones. Okay, but now supposing we consider and the usual homogeneous thing, and we consider linear transformations that preserve minus psi 0 squared plus psi 1 squared plus psi 2 squared plus psi 3 squared. Now it's easy to work out that because this is what the linear transformation preserves, the norm which is invariant under such linear transformations is actually minus 1 to the D, and then D factorial, A factorial, B factorial, C factorial, A, B, C, D squared. And this is important that there has to be this minus 1 to the D. Okay, but this is bad because once you have a norm, this is now not a positive definite norm. If you don't have a positive definite norm, it's the same as saying you don't have a unitary representation. So this is non-unitary. Now Dirac doesn't waste time in stray comments, but I'll make a stray comment that probably this is how you get the non-unitary finite dimensional representations of SO31 if you wanted to do it. This would be a way. You would, of course, still get the symmetric tensors, and with some extra work, you would get some other tensors. But in any case, the finite dimensional representations were long known. So again, it's not a new problem. But he observes that only with this norm, this construction works. So he says, no, we better do something new. So he does something new. And what he does is to write a new quadratic form, which I'll call Q. I think he also called it Q, which is summation A B, C, D, psi 0 to the minus D, minus 1, psi 1 to the A, psi 2 to the B, psi 3 to the C. And the restriction now is A plus B plus C minus D equals N. Okay, so this is the Dirac maneuver, if you like. And the norm which it preserves now is summation A plus B plus C minus D equals N, A factorial, B factorial, C factorial over D factorial, A B, C, D squared.
These need not be a finite sum now, right?
The sum is not a finite sum. It cannot be a finite sum because you have to take all A plus B plus C minus D equals N. So you get an infinite sum. And that's exactly the point. You better get an infinite sum, then only you will have an infinite dimensional representation. And the beauty of it is that infinite sum will give you a unitary representation because this norm is positive and it preserves this norm. Okay. So we get both. So that way, we get, I mean, the bug is actually a feature, namely the infinite dimensionality is exactly what you want because we know that we are only looking for infinite dimensional representations that can be unitary. This establishes unitarity, and this constraint establishes infinite dimensionality. And just to give you a little bit an example in the spirit of that one, here even the n equals 1 case is pretty non-trivial. And I'll leave you to work out the details, but I'll give you some answers. So now it's not the rank of the tensor, which is n, but it's what you might call the super rank, to use the language of supersymmetry. So for example, at n equals 1, you get, for example, A1000. Okay, now unfortunately, D is the fourth index. So fourth index is 0. So this corresponds to T1 by what I said earlier. Likewise, you get 0, 1, 0, 0. So you'll get T2 and T3. You can't have 0, 0, 0, 1 because then the sum of them is minus 1. But we want the sum to be plus 1. What you can have is something like this. T1, 1, comma, 0. 2 1s and 1 0. And I put a comma. Okay. So that means that A is 2 and D is 1. Okay, D is the number of zeros. You understand? So this component and likewise all the other components which have a single 0 afterwards, 220, T330, T120, T230, and T130. All of these satisfy this constraint A plus B plus C minus D is 1. Okay, this is here A is 1, B is 1, D is 1, and C is 0. I hope you can read off these things. So the general rule is you'll get tensors which have a lot of stuff and then a lot of zeros. So I separate the zeros from the 1s, 2s, and 3s. And the rule is that the number of these is 1 more than the number of those. Okay, so that the difference is 1. and now you're in business. So now it's going to go on forever. Later in the series, you'll have T with 1 million and one of these and 1 million of those. So it's an infinite dimensional representation. And Dirac, though he was not very particular about mathematical rigor when he didn't want to be, but I think he realized in this paper that it would be dead if he didn't talk about convergence of the things he's doing. And so he has a whole section on it, which I'm not going to report on, but I just to tell you that it is there. Okay. So that's Dirac's trick. And as you can see already in the case of O3, it gives you symmetric tensors in particular and non-symmetric also. But the point is that therefore generically his expansor representations are reducible because any symmetric tensor can have a trace of any two indices removed from it. So it will be reducible into lower dimensional representations. And he doesn't talk about what to do about that or how to get irreducible representations or anything. Basically, it ends here with also some speculations about application to physics, which I didn't really fully understand. But that part is accessible to all of you, so you can read the paper if you like and see if you can make it work. Yes.
If we take non-negative powers of 0,
Ah.
1 by d factorial.
Yeah, exactly. Yeah, exactly. That's the earlier comment will apply here. And in fact, I think I just misstated it. I don't think it's needed for O3, but it's needed here. In order to verify the invariance of this norm, you will get some extra factors which involve this norm. You'll get some extra factors here, but those will, when you shift D, but that will be 1 over some negative integer factorial, and that one you have to set to 0. So that's Dirac's expansor formalism. So it's a 12-page paper, and as you can see, it's easy to work out the steps very explicitly. So now I will switch to Harish-Chandra, but first I'll pause if there are any questions.
Dirac doesn't make any comment about
he says that they should exist and that it should be possible. He says they should exist and it should be possible to get them by generalizing this construction to spinors. And then he gave that problem to Harish-Chandra to solve. Now, Harish-Chandra could have done, so in fact, after reading his paper more carefully, even after day before yesterday, my respect for him has gone up enormously. I mean, based on this paper, I mean, all his future papers were terrific, which I'm not discussing. But this paper was not the thesis problem that Dirac assigned him, which would simply be take this expansor stuff and do it in spinors and go home. That's not, he made a goal higher than that for himself to classify the irreducible representations. Okay, and on the way to that goal, introducing expinors was nice, and he did that also. But it's maybe not the most central part of the paper. For example, he found the labels of the irreducible representations, which are infinite dimensional for SO31 by abstract arguments paralleling those of Weil and Cartan and people who had done it before for compact groups. Very, very textbook, like literally and precisely, and with a real mastery. I think basically van der Waerden's textbook was the root of. I think he had just eaten up that textbook and he just used that. And that part is very impressive because in the end he did what Dirac asked him to, but also much more. And it's the much more which put his paper clearly on a par with Bargmann's competing paper and Gelfand and Naimark's competing paper. And he was the first of the three. Well, he was 1 month earlier than Bargmann to submit to the journal, which didn't mean anything in those days. I mean, that was the speed of transferring information from US to England and between England and US. And from Soviet Union, the speed was much slower. So we actually don't probably have details of when Gelfand and Naimark did their work, but clearly they were all independent. Okay. So now any more questions or any questions about anything that I've done so far? Okay, so now I will actually, and I could have saved it for now, we will actually use this way of labeling representations, which was J1, J2, JM, sorry, M1, M2, or J0, J1, JM. So remember, the first two label the irreducible representation, and the second two are things which vary over it. Okay. Now, the question is, what are the values of these things? And the answer, so J0, I'll remind you, was J1 minus J2, and J1 was J1 plus J2, and J is any integer or half integer in the range J0 to J1. So when we do this inequality in this subject, we always assume that the shift from here is integer. Okay. And okay, so probably I'm already assuming something. No, I think this is okay. And M is between minus J and J. The crucial step for the finite dimensional representations is to now impose that J1 and J2 small are integer or half integer. Then we get finite dimensional non-unitary representations. So what do we get in general? So the answer, and a beautiful feature of Harish-Chandra's paper, I would say very mature actually, and which should have earned him more citations than it did, he summarizes his conclusions right in the beginning. I'll do that in this notation and then just tell you what his notation is, which took me a while to penetrate, but turns out actually to be the same. So there are two series of representations. One is called the principal series. And in this series, J0 takes the values 0, half, 1, okay? And J1, however, takes the values -1 minus I rho, where rho is real. So now you see that J1 is no longer integer, or half integer, and it's not even real, it's complex. Okay. And then J, which is supposed to lie between these two, now it becomes a bit complicated to lie between a real half integer and a complex number. So it only satisfies the lower bound of that. So J starts at J0, which was J min, and J0 plus 1, sorry, J0 plus 1, and then just goes on forever. If you remember how, if any of you has worked out the calculation of finite dimensional representations, you'll know that it is this max value where it sort of ends. Okay. And here, since the max value is not real, there's nothing to stop it and it just goes forever. So that makes it infinite dimensional. M we don't mention because M is always, since J is like this, M is between minus J and plus J as always. So this is the principal series. And the other series is called the complementary series. And in these names were not given by Harish-Chandra. I wanted to check if they were given by Bargman, but I didn't have time. In this series, J0 is 0 only. But now, J1 is so, and J1 is again like this. But now rho is imaginary. So J1 is actually real. But it's negative. So it's still not anything like the unitary ones. And the constraint on rho is that minus I is less than rho is less than I. So by this, I mean that rho is on the imaginary axis and it lies between these values. So many authors first redefine rho to be I times another rho or something else, and then that is between minus and plus 1 or something. So this is the second series. And in this series, J, which is supposed to start from J0 and go up in integer steps, doesn't actually take the value 0. It starts at 1 and then it goes up to infinity. So both are infinite dimensional. Clearly, what you need for infinite dimensionality is that the range of this pair is infinite. You fix this pair and then you ask what's the range of this pair. If that's infinite, then your representation labeled by these two numbers has infinitely many components labeled by these two numbers. Okay, clear? Now, of course, I haven't derived anything for you. So now let me try to sketch. I certainly won't be deriving it. It's a very, very dense paper to read, but there are various steps, and I think I could appreciate roughly what he was trying to do. So before I get to the steps that he performed, let's also just write down our Casimirs because he makes use of those. So C1, recall I said that it is J squared minus K squared. Just to confuse things, Harish-Chandra refers to J as K and K as L. So it's very complicated to read that. But anyway, and it is, yeah, it is this. And it's equal to J0 squared minus rho squared minus 1. You can easily derive this. Oh, I forgot to say something here. I forgot to say something here, and then I'll go back to that. So given these principal and complementary series, I've given you the values of capital J0, J1, J, and of course M. But what are the values of small j, J1 and J2? I mean, we can just read it off, and I think I should tell you that. So the values are, if J2 is greater than J1, we have to pick one of those signs in order to determine J0 because J0 is a mod. So I'll just take this, and then there's an obvious reflection to get the other one. Then J1 is equal to, yeah. So of course, both are complex. So you may ask how they can be greater and or less than each other, but turns out they have the same imaginary part. So you can actually compare them. So their difference is real. And J1 is half times minus 1 minus I rho minus any of these numbers. And notice that this contribution now can be a quarter integer because of this half in front. J2 is the same thing, but plus this thing. And there's an added restriction, which many textbooks don't bother to mention, which is that, okay, this can be a quarter integer and this can be a quarter integer, but the difference of these two numbers has to be a half integer. I could have, so if this was, if I pick half from here, I can only pick half, 3, half, etc. from here. If I pick 0, 1, 2 from here, I have to pick 0, 1, 2 from here. So that the difference is half integer or integer, not quarter. So J1 minus J2 is in. That's an extra restriction, but these are the values of J1 and J2. And from this, I can, of course, immediately compute the Casimirs because J1 and J2 are the values for M and N. So I take this JK and I rewrite in terms of M and N, and then I work it out and I get this. And likewise, C2 is what? Is minus rho times J0. And by the way, C2, there's a sign ambiguity in C2. If you remember, C2 was in terms of the original SO31 generators, it was an epsilon symbol for component epsilon symbol times mm. But that epsilon symbol always has a sign ambiguity. By a parity, I can go from one to the other. So anything which has an epsilon symbol, you can't a priori be sure of its sign. You have to fix the sign by convention. And so it's as good to take this minus as plus. And that's why I've given the range of rho in this series like this. So rho to minus rho will interchange this half with this half. So actually they are equivalent. So some authors give rho between 0 and I or minus I. Okay, good. So, as far as these j's are concerned, from this you can see right away that J1 plus J2 is minus 1 minus I rho, which is exactly J max. And J1 minus J2, that drops out and you get half times this series. But because of that constraint, you actually get this series only, which is exactly that. So this is the sense. Okay. And in Harish-Chandra's notation, he has, again, very confusingly, two labels for his representations, kappa and kappa star, but despite the star, they are not complex conjugates of each other. In fact, they are actually our friends J1 and J2. So you can read his paper with this fact. And I think one more fact you need to know is that Harish-Chandra's mu is minus rho by 2, or it could be plus rho by 2. So if you are with these things, then you can translate everything from his paper. There's also a question of multiplicities, which I won't go into, but okay. Now let me sketch his derivation and then I'm basically done. So good. Any questions on this? This is the results. These are also the results of Bergman and of Vogelfand and Naimark, because they are the true answers for the unitary irreps of SO31. What clarified in my mind after working this through for this talk is that, there's no question of his results being implicit. They are out there on page 1. So, I mean, Sachin wasn't here last time, but he has 30, according to Google Scholar, he has 32 citations, while Bergman's competing paper has 1600. Okay. So, now there could be issues with Google's databases and all, but probably it's the same database, right? People who use this stuff. So somehow one made it big and the other not so much. Okay, good. Yes, J0 is fixed to be 0 and it doesn't change. So in that series, J can still take infinitely many values. So it's still an infinite dimensional representation. And rho is imaginary, which makes J1 back to real. But because of the restriction on rho, J1 is negative. So again, it doesn't terminate this series. Normally it would be a positive value would cause the series to terminate. But J1 is negative, so it doesn't terminate the series. So this completes. These are all the, this completes everything except that for some cases, there are two distinct representations. So that is the multiplicities of representations, which I can't go into because I think it would make the discussion too tedious and detailed. Apart from that, these are, I mean, this characterizes all unitary representations of the homogeneous Lorentz. Okay. So a quick summary of his process. Sorry, keep using the wrong duster. So the first thing he does is actually to use this reduction procedure. So last time we discussed that SO3 is not a normal subgroup of SO31, but certainly you can if you know representations of this, you can reduce them to that. And in his case, you don't know the representations, but you can still use SO3 labeling, which is exactly our J1 and J2. So you just use that labeling. And what he does is to compute. So the states of this one are J, comma, M. These are the unitary representations of SO3. And so using standard techniques of raising and lowering by J plus and J minus. So first he defines J plus minus. So these J's are the J's of the Lorentz group, forgetting the K's for now. And they're also the J's of that diagonal SO3, as I explained earlier. Okay. So now he has relations like this, Jm sandwich. So these are all standard manipulations in SO3. This is the same as this. Maybe I won't write the ones for J minus. I'm just going to focus on relations for J plus, and there are always analogous relations for J minus. But I'm sure you have seen this. This sort of relation is what tells you that J plus has to stop raising after some point, and acting on the left, it will stop lowering after some point. So these things. Okay. So this kind of relation is known from SO3. So first we borrow that. Now we ask for analogous relations involving K. And I'm going to write only the relations for K plus, defined in the same way. So now we are talking of the Lorentz group or Lorentz algebra. And now we can only use one fact about K for the moment, which is that it transforms as a vector under J. So if you remember, the commutator of J with K was again K. So that's the statement that K is a vector under J. If you think of J as acting and K as being acted on, then K comes back, and that's exactly what a vector should do. So, so it's a vector, and that alone is enough to fix the matrix elements up to a function overall, depending only on J. So you have relations like J, M, K plus. Now, a general vector operator can cause transitions between different J's. So capital J only connects the same J, but K can connect J minus 1 to J, or J to J minus 1, or J to J. Three possibilities exist. Again, it's well known in quantum physics because these govern the kind of transitions you can see in atoms. So this one, for example, is labeled as minus P minus of J. So P minus is an unknown function which this symmetry argument cannot fix, and he's going to try and fix it. Apart from that, it has again a similar square root form, J plus M, J plus M minus 1. And there's a similar formula involving J. I won't write all the formulae, but the same operator, but now on the right side, I put J and M minus 1. And then in the third case, I put the same operator, and on the right side, I put J plus 1 and M minus 1. So what a general vector does is always to raise M minus 1 to M. And with given J minus 1, it can raise it to J. Given J, it can keep it J. And given J plus 1, it can also lower it to J. These are all possible. And the coefficient functions in each case are special to the operator in question. But then there's a known square root similar to that with some J and M things. Okay, except the coefficient functions are P minus for this one, P for this one, and P plus for this one. Okay, so this is the first observation. In fact, if you think this one is a special case, if I put, because this applies to any vector and J itself is a vector. So if I put J here, then this middle one is the same as this relation, and so P of J is 1. And if I put it here and here, P minus and P plus are 0. So that's a special case. Okay. Now he evaluates, so this is step 1. Write these relations after reducing SO31 to SO3. Now step 2. So recall that C1 is J squared minus K squared. These are the two Casimirs. He brings them in now. And he says, well, we can evaluate these in terms of J and M. And of course, the unknown functions, P minus, P and P plus. This P has nothing to do with momentum. These are just three functions. So how do I do that? Well, I take these and I sandwich them. So these are Casimirs. So they are diagonal. They commute with everybody. So they are diagonal. Okay. But now if I sandwich, but they are also quadratic. So let's look at J dot K. I sandwich it between JM and JM. Okay. Then I can ask what's the intermediate state? Well, K can take JM on the right to only three possible choices. Okay. And then J has to take those three possible choices back to J and M. And all those matrix elements are given there. So you can evaluate both of these in terms of two numbers and three functions. Doesn't look like we've gained a lot, but anyway. Now there's a bunch of consistency conditions for the resulting formulae. It's very beautifully done, and I would say it's very mature considering this is a PhD thesis. So step 3, is consistency and unitarity. So that actually enables him to fix these three functions up to a finite number of parameters, and those parameters turn out to be our friends capital J0 and rho. And then, so that's, yeah. And in fact, what he gets in the end, you can take his formulae, and if you rewrite them in my notation, he gets exactly this. And the way he writes it is that rho squared is greater than -1. Now, this is a weird relation, because if rho is real, then of course rho squared is 0, greater than 0. So it doesn't really, this relation tells us nothing. But if rho is imaginary, then rho squared is less than 0, and then it must be between -1 and 0, which is exactly the restriction -I less than rho less than I. Okay. So if it's imaginary, it's this. If it's real, then it's any real number. Okay. This is what he gets in general. Then he reads off from this that, well, there must be two series. One is where J0 is non-zero. Now, if J0 is non-zero and if this has to be real, then rho better be real. That's the principal series. But if J0 is 0, then rho doesn't have any constraint from this equation because C2 is just 0. But J0 is 0 here. And then he argues that C1 is bounded, which gives this bound on rho. And that's the complementary series. And then he also works out multiplicities and certain values of J1, J2 for which you have two representations, certain for which you have one, and that's it. So that's the first half of his paper. And then at some point so this is a constraint on rho. He still hasn't got the constraint on J0, which is also crucial. And then he does some more work to get that. So I really don't have either time or energy or even maybe ability to summarize all the work. But basically, by now, I hope you're getting used to these formulae. And this is sort of the story. So last comment is that the generalization of expansors that Dirac worked out. So expansor comes from expansion tensor of expansion or something. So of course Harish-Chandra quite cleverly proposed to label his thing expinors. So it's instead of tensors, the role is played by spinors. And roughly what you can imagine is that, well, we introduce spinors U alpha dot. So this is U1, U2, this is U1 dot, U2 dot. These are the spinor representations of the SU2 labeled by M, and this is the SU2 labeled by N. Okay, and you introduce all of these, and then you can take formal series with U1 to some alpha 1, U2 to some alpha 2, U1 dot to some beta 1, U2 dot to some beta 2. So they play the role of that psi 1, psi 2, psi 3, and psi 0. But it's not that simple, actually. And in fact, this part of his paper gets horribly technical, because if you just do this naive expansion with some coefficient here, it actually doesn't work. And you, in fact, get a non-unitary norm that this preserves. Because spinors have a different norm, and you have to be very careful to make it positive. So in the end, he has to do something funny like divide by a power of U1 dot plus U2 dot to some power. So it's very complicated. Okay, but whatever it is, he works it out, and he shows precisely that the representations. He also shows the irreducible decomposition of these, and shows that they exactly map to these predicted values of J0, J1, and rho, which label the representation. So it's like a complete discussion of the subject, including what Dirac assigned him and also what everybody would have wanted to know who was interested in unitary representations of the Lorentz group. So with that, I finished. So I'll stop here. Thank you. There's any further differences?
Why do you say there are no physical applications of XO3?
No, of the unitary representations of SO3, 1. Unitary. Irreducible, okay, you can make them reducible. They are infinite dimensional. So yesterday I went, or last time I went into this a little bit. So basically, and by the way, I would like to recommend a textbook on group theory by this author, Mukhi is the only textbook. It's again group theory for physicists or something. It's quite accessible for us and it's quite precise also. But is the only one I think where he has given a detailed description about the relevance of representations of the Lorentz group, finite dimensional. So there are three things of interest. So one is finite dimensional, non-unitary, and SO31. The other is unitary, infinite, also SO31. And the third case of interest is unitary, also infinite, but of ISO31. Now, the interesting fact, so broadly, if you say these are important, why? Because the quantum states of a quantum field theory, they are normalized and they better have when they transform under a Lorentz transformation, they better remain normalized. And so it has to be this representation which acts on them. Okay. But fortunately, they have a label P, the momentum of the state, the total momentum for momentum. And because that is there, we are in ISO. And because we are in ISO, the whole picture of Casimir changes. There's a concept of little group developed by Wigner and then Bargmann-Wigner. And then you can work it all out and you have infinite dimensional representations. But the infinite part, roughly speaking, comes from this P, this momentum. Okay. So this is for states. On the other hand, as soon as we open a QFT textbook, we are taught that the possible fields you can put in a Lagrangian of quantum field theory or classical field theory, if it's relativistic, are scalar, spinor, vector, spin 3/2 tensor. So what is that? Those are the finite ones and they are not unitary. So it's the non-unitary finite ones which act on fields. And that leaves no use for these ones. They are neither the ones that act on states nor the ones that act on fields. If these were to act on fields, then they would have to be infinite component fields. Okay, they could not be a field with just 2 or 3 components like a spinor or a vector. It would have to be infinite component. If it was to act on a state, the paradox is you would only get states which have zero momentum. Bargmann makes this comment. So if all states are going to have zero momentum, then your quantum mechanics is pretty useless because there's no time evolution. In fact, I think he even mentions we don't mind so much if the space evolution is trivial for some reason, but time evolution being trivial means like everything is frozen and there's nothing to do. So it's pretty useless. So that's why these remain in a question mark. That still leaves a puzzle which you should actually ask me and which I have been puzzling for years. And actually, this is the reason I agreed to Devendra's request to give these lectures. I wanted to sort it out. How can it be possible that these transform in finite representations, these transform in infinite representations, but these acting on the vacuum produce these? And the trick is, and as it's explained in this book. Now, Weinberg's textbook QFT1 had the opportunity because he does discuss these and also these. But I don't know if he really explains this precise thing, but this guy has a section called relation between representations on fields and representations on states. And here, between these two, the key step is that you go from fields as functions of x to the momentum space to get the creation and annihilation operators A and E dagger of P, and that's where this group comes. So somehow it happens automatically. It's compatible to have the fields be in finite dimensional non-unitary representations, but the states be in unitary representations of a different.
That finite dimensional representation acts in the continuation space of the field, while that acts on the Hilbert space.
Yes, that's correct. But the field, when it acts on the Hilbert space, creates this state, right? I mean, in our mind, the field acting on vacuum creates a one particle state.
Finite dimensional representation acting and unitary.
No, so here we have something which transforms in a finite representation, but now I'm acting with it on a vacuum. Okay, now what is the result? The result is that of whatever state the operator takes the vacuum to, but should be a one particle state. But actually, the one particle state we discuss is the one in momentum space, not in position space. So we don't literally ever work with the state phi of x on 0. We first decompose phi into modes, and then we let each mode act on the vacuum. Okay. And in that process, again, I can't tell you the details here, but I can just tell you that it's explained here in precise formulae, that this then becomes, the consequence is that though this transforms in this representation, the whole state in the momentum basis transforms under these unitary representations of ISO, and therefore they preserve the norm, which is crucial. This also, by the way, gives rise to things which we know in field theory, like the inner product of states has that root 2e factor and all those things. Everything comes out from this discussion.
These are not useful.
They have not been useful so far. However, there is one observation I can make, which is that if I have de Sitter space in 2 dimensions, 2 plus 1, then its symmetric group is SO3, 1. Okay. If I have de Sitter space in 3 plus 1 dimensions, then its group is SO4, 1. So whatever we know about representations of these algebras or groups can be transported to study representations of the de Sitter group. And actually, there are a few citations to Dirac's work from people like Penedones and so on, who I think the physics people here at least know about, who are working on some S matrix, bootstrap, and things like that. So just to say that, you know, it's not all hope is lost. Maybe these will come into physics, but from an indirect route, not dealing with Minkowski, but with, good question. I think it's it should be now with all these lessons. I think it should be straightforward. Bargman actually took so as you know, this work was done independently by Harish-Chandra, Bargman, and Gelfand-Naimark. But Bargman's paper is really on SO2, 1, which happens to be SL2R. So the paper says that I'm going to talk of these two groups, but most of the work is done for this one. So we now know one lower dimension, which is good because actually, if you know this, it's not so hard to work out this one. Because it has this very similar features to this, except there are not two J's, J1 and J2. There's a single one which takes these kinds of weird values with some complex numbers. And so now SO4 and higher should be doable, and if it's not done, certainly it should be done. But again, expansor probably may not be the way to go right away just thinking, because it will give you reducible representations, which you probably could have worked out otherwise also. But Harish-Chandra's method surely can apply. And I suspect somebody has done it. Yeah.
So why is that just an integration over all momentum space?
Yeah.
And momentum space you said transform under
yeah, exactly. Yeah.
This space you also transform
no, so that integration does something. So I don't want to say here the details because I don't even remember them well. But that's it's all in the details of that process of going from phi x, doing that momentum integration, everything is what really takes you from that to that.
So the transformer two dimensions, why don't we use this representation of all these the series and complementary?
Yeah, because SO21 is SL2R. So, and conformal field theory uses SL2R cross SL2R. That's why, yeah. Yeah, I guess so. Good question. Why not? Again, because, you know, with conformal field theory, we normally, yeah, why not? Actually, I don't know.
So you were already trying to cover in the context of DSP, right? So then,
yeah,
we do that, so that we have to do.
Correct. I agree. I agree. So the point is that now with the interest in the physics community in ADS and DS type spacetimes, these representations probably have some role, and maybe they have even played some role. So all I'm saying is that in the context that was known at the time and after that till last maybe 20 years, no concrete use was found for this unitary representations of SO2. I see. Okay, that's interesting. Okay. There's actually, if you know the author, do let me know, then I'll look it up. Yeah. Okay. If I can tell it. Yeah. Okay.
So you were mentioning something about quantum mechanics while describing K.
Yeah.
What was that?
Yeah. The statement, well, the statement, it doesn't rely on quantum mechanics. It's a statement that anything which transforms as a vector under J, its matrix elements are given up to overall functions which depend only on J and not on. And so these square roots, they are there in the calculation, but exactly what they are is not so important. Important is that these functions are determined in terms of J and M in this simple way, but these functions are not determined by that fact.
So was there any analogous operator quantum mechanics?
Yeah, because in quantum mechanics, we have lots of vector operators. You know, any kind of vector that crops up, it could be a vector potential or anything. If I want to evaluate its matrix elements, before doing anything, before knowing what its physics is, I can write this. This is true whether it is K or J or anybody else. But of course, if it's J, then it's more special. We know much more about J itself. And there P minus and P plus vanish and P of J is 1. But if it's anything else, we can immediately write this. For this, he cites Y. So this is, yeah.
Small j are basically capital J, right?
No, these small j are small j. These are, these small j, good. Maybe that's right.
I think you mentioned SO3, that's why it is used small.
Yeah,
J.
yeah. So sorry. So these are SO3 states. These states are states of SO3, not of SO31. Okay, because when I study a group SO31, I'm free to reduce it first. So this is the reductive method with representations. So I can reduce it to the SO3 subgroup of SO31 and then do these manipulations. I don't give any physical meaning to this. I just use these to determine the Casimirs in terms of those states. So if SO3 is working for me, I can use it. That's basically the philosophy.
Okay.
Yeah.
So let's thank Sunil again for this excellent talk.
Thank you.
Also, I think since this is the last talk for this time, let us also thank all the other speakers. And also
and the organizer, Devendra, who has done
excellent organizer.
Yeah. And Devendra has really worked insanely hard with this. I think it's one of the most well publicized activities here. And I wish more people actually from mathematics. Nice that a few theory physics students here, but I wish more mathematics students would have come for this series. And I hope they will next time. Okay, thanks.
You said you had a story to tell about Wigner, right?
Yeah.